Hello everyone, thank you for your participation. Today I'm talking about spin-orbit coupling, that is the merit of Dirac equation. So first, what is spin-orbit coupling? That's a kind of two-particle interaction whose potential or Hamiltonian term includes the so-called LS product. So it's symbolically written as this HLS, which includes first the wildcard part x and L dot s. And here L means orbital angular momentum and s is the spin angular momentum and j is the so-called coupled angular momentum. Okay, so first you may ask that why do you take this strange or crazy stuff? Is it tasty? Indeed, this potential looks a little bit complicated, and if possible, one would want to avoid to fight with this crazy term. However, fortunately or unfortunately, so first, it's not tasty, but that is important for atomic and nuclear physics. So next, let me talk a little bit about the background in the atomic and nuclear physics, where or why this crazy spin-orbit coupling term has been needed. So first, background 1, fine structure of atomic spectra. Traditionally, to explain the atomic spectra, Schrödinger equation has been utilized. And this equation approximately explains the atomic spectra, which is well known as this En, and here En includes some symbolic quantities in atomic physics, that is fine structure constant and electron mass. And this result is not bad. However, in the super accurate measurements of spectra, there is a finite branching into some levels that is called fine structure. Namely, this En has a small but finite branching, and to explain these split levels, we need some corrections. That is, from the original Hamiltonian zero, we should additionally employ the spin-orbit splitting Darwin term and also the relativistic correction terms. So that is the first background why the spin-orbit splitting as well as the other corrections have been necessary in the atomic physics. And the next one, background 2, spin-orbit interaction of nucleons. Okay, let's change our focus into the core in atom, that is the atomic nucleus, and this is the many-body system of protons and neutrons. And for this many-body system, the so-called magic numbers are well known, that is 2, 8, 20, 28, 50, 82, and 126. When the number of protons and or neutrons is equal to one of those numbers, that nucleus becomes more stable than other cases. Okay, this is empirically well known, but how to explain this property? And indeed, to explain these magic numbers, the spin-orbit interaction again plays an essential role in this way. The mean field potential for a single proton or neutron is given as this Vr, which includes the central potential plus the spin-orbit interaction. And actually, this work was first done by Goppert, Meyer, and Jensen, and after they got a Nobel Prize. So, the Schrödinger or Dirac equation. And here, first we focus on the time-independent solution in both cases. And then first Schrödinger equation, that is in the non-relativistic limit. Okay, it works, but phenomenological corrections are additionally needed, as I told in the previous slides. On the other side, there is one another option to explain the atomic spectra or nuclear physical properties. That is Dirac equation, which is in the relativistic case. And indeed, this Dirac equation can naturally explain the spin-orbit term and Darwin term and non-relativistic corrections, blah blah blah. So the goal of operation today is simple. That is, to show how the Dirac equation naturally explains this spin-orbit coupling, Darwin term, and relativistic corrections. Alright, so now I've changed to my note here. So first, let me introduce my convention for Dirac formalism here in table 1. First, I utilize these flat matrices of plus, minus, 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 and for the coordinate and for the derivative terms are given as this. And okay, I employ the well-known sigma matrices for spin algebra and also the gamma matrices. Next, the Dirac spinor for spherical system is generally given as this equation 9. Oh, sorry, equation 9 here. Yeah, and here the capital Y is the coupled spinor with orbital angular momentum part and spin algebra part. Alright, then now I start my main part, that is the Dirac equation with spherical potentials. So we assume the 1 plus 3 dimensional time and space. So in the MKSA or CGS Gauss system of units, the Dirac equation is given as this equation 17, which includes the scalar potential SR and vector potential WR. So, okay, before solving this equation, then let me note that from these formulas, the equation can be also expressed as this form. And from this equation, you can infer that the Lagrangian density, which works as the source of this equation, should be given as this. And some of you already know this form really much. And for note for dimension, and that is not directly important in this talk, but because the Lagrangian have the dimension of energy, psi by psi is in the unit of Fermi inverse third, or equivalently the inverse of the volume. As coincidence, if some interaction has the form like this, then this wild part x must have the dimension of energy, for example in MeV. And this knowledge may help us, for example, to infer the unit of the coupling constant. Okay, next into the two large and small components. For the time-independent solution, that is, symbolically given as this, the Dirac equation reads this form in the time-dependent version, and this Dirac spinor for the spherical system is generally given as I told before, this form. And here, capital Y is the coupled angular momentum state. Okay, then, by utilizing the spherical solution ansatz, the original Dirac equation is transformed as these two equations for a large component Fn and small component Gn. So before going to the further calculations, now we focus on the first term, or the operator here, sigma dot nabla. By using this identity, then this sigma dot nabla operator becomes blah 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 blah, and finally in this form in equation 27. And here we have used the well-known convention for spin angular momentum and orbital angular momentum. Namely, here we already found that the spin-orbit coupling is naturally concluded from this kinetic term in the Dirac equation. However, of course, as we will see later, if the gap of potential, that is SR minus WR, is constant, this spin-orbit term vanishes. Now, from the two equations for Gn and Fn, let me eliminate Gn. Then, the corresponding large component reads this equation 29 here. Okay, which looks a little bit complicated, but okay, anyway, this is now the equation only for Fn. So, okay, in the following part, we use this epsilon En defined as this, okay, this denominator part indeed, and also I skip this I in the following. Then, because sigma dot nabla squared is simply nabla squared, it becomes that this equation 30. In the next, for the second term, namely this term, let me notify that sigma dot nabla operating on the 1 over En is this, and also the sigma dot nabla operating on Fn is simply this. So, by using this technique also, this last equation is transformed as, again, a little bit complicated form here, but it's almost done for today's goal in this talk. That is the final form of the equation for Fn reads this equation 32, which includes, okay, the first term in the left hand side corresponds to the kinetic energy, and the second term is so-called Darwin term, and this third term here indicates the spin-orbit coupling. And these Darwin and spin-orbit terms can be naturally concluded from the Dirac equation as I have shown. Alright, so, and it is also convenient to find that the total potential here is given as just the sum of S plus W. On the other side, the spin-orbit term and Darwin terms depend on this epsilon dash, which is nothing but S dash minus W dash. Thus, even though the total potential is 0 or very small, it does not guarantee the free condition for fermions. And of course, remember also that for the spin-orbit coupling term, this is well-known formula, depending on which J coupled with L and S. And finally, from Dirac equation to Schrödinger equation, the correspondence between this equation 32 and the Schrödinger equation is obtained as follows. First, we assume that scalar potential is 0, namely only the vector type potential is finite. And this is, for example, the Coulomb potential mediated by the photon vector field is only considered. Then second, in the non-relativistic limit, that is En minus potential is simply approximated as mass c squared, and thus epsilon n is just 2 of mass c squared. And of course, the E and dash is simply W dash minus. So finally, the last equation is approximated as this well-known form. And here, the first and fourth terms are well-known kinetic and potential terms in the Schrödinger equation, whereas the second term is the Darwin term and the third term is the spin-orbit coupling term. So, congratulations indeed. We found that the Darwin terms and spin-orbit coupling terms were naturally concluded by solving, okay, actually it's not really solving, but playing with the Dirac equation. After note. So we have found that the Dirac equation with scalar and vector potentials is given as this form. And unfortunately, the analytic solution is not available in general because sometimes you encounter with really complicated forms of SR and WR. So in that case, numerical computation is the standard way to solve this equation. The second, for the free fermion with S and W potentials are zero, then the analytic solution exists. And here I just give the form of the final solution, and there are two solutions for positive and negative energies. Alright, anyway, we found some complicated stuff for Dirac equations, but I believe that the knowledge you obtained today here will be helpful for your future studies. Thank you very much for your interest.